This video is about this calculator, developed in the 16th century, possibly by Galileo. The calculator not only made math easy to calculate, but also made math easy to understand. In presenting this, my essential point is that it is possible to delve deeply into math, science, and technology, knowing very little math and very little technology. 95% of science, math, and technology can be done with the right 5% of the tools, techniques, and principles. The historical approach used here is helpful because science was simpler at the beginning. The tools of the 17th century were simple and were used in simple ways. The tool had to be simple to make, to use, and to understand. I believe playing with this one mathematical tool led to much of our mathematics and physics. An interesting example of this is the development of universal gravitation. In order to study gravity, Galileo obtained the idea of using inclined planes to slow the fall of objects. Things fell too fast to allow measurements with primitive instruments. Rolling weights down an incline slowed the process down. His slowed down measurements led to the idea that the distance fallen was proportional to the square of the time. The essential idea of using the inclined plane could arise naturally from Galileo playing with his calculator, since his calculator is not much more than an inclined plane with numbers on it. Modern students would benefit from such play today. I think any play with something you hold in your hand is helpful. Muscle memory, visual memory, and language all play a huge part in any mathematical activity. In a digital computer, almost all activity is entering numbers, formulas, and programs. All numbers, formulas, and programs tend to look alike. Typing is typing, whether typing math, writing the great American novel, or stirring up conspiracies on Facebook. The muscles work the same way, always. Because typing all looks and feels the same, many think they've accomplished something when they add .003 to 1000. But your answer isn't correct. You haven't added in the .003, they say. Adding with a ruler and pair of dividers shows the folly of this. Adding with a calculator or spreadsheet does not. Let students have a wide variety of math experiences, from the abacus, slide rule, drawing pictures, or playing with the calculator that Descartes, Galileo, and Newton played with. Since Descartes, Galileo, and Newton founded the modern scientific world, playing with their calculator may have special power. Students also need to be encouraged to master a few simple tools instead of trying to do everything. One good mastered math tool can do almost all the rest of mathematics. Just as addition can do what multiplication does, any math well understood can do all math. The tool to start with is the use of proportion. A proportion states a problem with is to, as, and another is to. A is to B as C is to D. Or 6 is to 3 as 2 is to 1. Thinking in terms of proportions, as the ancient geometers did, often gives a better view of a problem. It is fair to say that proportion underlies at least 80% of all scientific formulas. Galileo's pocket calculator which is called a sector, by the way, is all about proportion. The sector uses simple linear scales and the proportions from a similar triangle to make calculations. With a pair of dividers, the simple sector can add, subtract, multiply, divide, calculate reciprocals, measure angles, and calculate the chords of circular arcs. With an added square, trigonometry becomes possible. It is also a handy drawing and measuring tool. While basic arithmetic is easy with the sector, the list of more complicated mathematics it can demonstrate is amazing. The number line with positive and negative numbers is right on the open sector. Here is the Cartesian coordinate system. Here is the slope of a line. Here are the cosine, sine, and tangent. Playing with a sector can help visualize vectors, projective geometry, transformation of spaces, and concepts in statistics. I wanted to just show pictures of some of the wonderful old sectors from the museums, but the museum sectors are too complicated and don't photograph well. The old sectors were a mass of lines and marks. All the scales usually on a slide rule were present, plus anything else the designers thought useful. A mathematical tool in the 17th century had to do everything because one tool was often all you had. To make this as simple as possible, I built my own crude sector with just 3 easy-to-read scales. The front has 2 identical scales of equal spacing, numbered to 10. The back has a scale for measuring angles to 60 degrees. As in a slide rule, the sector doesn't keep track of the decimal point. Multiplying or dividing by 10, 100, or some other power of 10 is usually necessary. In general, scientific notation is still usually the easiest method of keeping track of the decimal point. Here I am building, cutting the rough shape. Rough milling. Filing to final shape. Drilling the hole for the hinge. Building a half-circle gauge to put 0 at the center of the hinge when graduating. Graduating with gauge blocks. The scale length is 5 inches, so each digit is half an inch. I generated the scale of chords with a dial caliper and a table of chords, multiplying each entry by 5. Here's the final result. So to multiply 2 times 3, we can set two out here at 10. Then we come down to 3 and obtain a measurement, which is 0.6. So we multiply that times 10, we get 6. If we want to divide 3 by 2, we take we want to divide 6 by 2, we take the 2, the divisor, and we set it out here by the 6. Now we take the 1 we run it down here, and it comes opposite the 3. To obtain the reciprocal, say we want the reciprocal of 5. We take 5, put it out here at the 10s, and then we take 1, we run this down, and we get it to 2. Now the reciprocal is not 2, it is 0.2, so we have, since we were out here at 10, we have to divide by 10 and obtain 0.2. To obtain an angle, on this side we have the line of chords, so we can take, say, 30 degrees right there. We put that distance here, and now we have 30 degrees. Which we can verify with this protractor. Or, if you want the sine and cosine, you can do that here. This square has parts marked off the same way, and I can come out here and you can see the sine is 5 over 10, or 0.5, and the cosine, I'm not quite square here, the cosine is a little over 8.5, actually 8.6 over 10, or 0.86. If we take a calculator and we put sine 30 degrees, we get 0.5. If we take cosine 30 degrees, we get 8.6, almost 8.7. So you can see, you can get trigonometry, you can also get the tangent. It's a little more difficult because you have to get the tangent, you would have to come out here and continue up with a straight edge of some sort. And we get about 5.9. So if you do tangent 30 degrees, 5.7. So you can see, you can actually do quite a lot of math here. Build a crude sector and play with it. You may find all mathematics becomes more sensible. Thank you.